Cool. So I'm Rosie Robertson, and I work at the Global Sustainability Institute, research fellow there. And firstly, thank you so much for coming. It's fantastic to have a completely full room. So that's brilliant. I thought I would just spend a couple of minutes introducing Emma and Erica and how I know them, who are our two speakers today. And then they are going to be debating the question, how useful are climate models? So we've gone for a slightly different format for those of you who come to our previous talks. Emma is going to be sort of giving the case for climate models and telling us a bit about what they are and why they're useful. And then Erica is going to be giving some of the counter views and saying what's wrong with them and some of the downsides, and then obviously open it up to questions at the end. So we hope we'll have a bit of a debate going. Just to introduce both of them. Emma is a PhD student jointly, I think, between the Department of Applied Maths in Cambridge and the British Antarctic Survey, and Department of Applied Maths is where I did my PhD, so that's partly how we met. But we also met because Emma's supervisor is Dr. Emily Shuckburgh, and I've been working with Emily on a project around how climate science is portrayed in the media and whether it can be improved to better engage the public, whether it can be explained better, basically. And Emma's also helped on that project as well. Yeah, do come in and see. And then Erica I actually known for quite a number of years, so I don't know if any of you came because of the plug I gave this seminar on Friday's event when we had our MP speaking at an event. Erica and I first met when we were doing a project, both doing summer projects with Herbert Huppert, who is Julian Huppert's father, who is a professor at the maths department, and we both do summer projects with him. And Erica was working on carbon dioxide sequestration, so she had a big tank full of glass beads to try and model. Carbon dioxide sequestration is where you try and push carbon dioxide underground to get it out of the atmosphere. And so Erica was modelling that. I was doing a lab project modelling ice flow in Antarctica. So I had a tank full of golden syrup that was supposed to be modelling the ice. But then we also did our masters together and stayed in contact. Erica's doing her PhD at the Grantham Institute at Imperial College London. Without further ado, I'm going to hand over to Emma. Thank you very much.
Thank you very much, Rosie. As Rosie said, I'm going to be arguing that climate models are the answer, with the slight caveat if you ask the right question. So as Rosie said, I'm doing my PhD at the University of Cambridge in the British Antarctic Survey, and I'm currently in my third year, and the area of my PhD is physical oceanography. So here's a quick outline of what I'm going to talk to you about in the next 20 minutes. First of all, I'm going to explain the difference between weather and climate, which might seem a bit basic to some of you, but it's important to understand what a climate model is. So that's what I'll tell you next. What is a climate model? And hopefully, if you understand what a climate model is, it will become clear exactly what questions they're good at answering and what they can't answer. And finally, I'll end on a little note that data isn't perfect either. So to begin with, weather versus climate. So, weather is really something that's short-term. It happens on days to weeks, and it's extremely variable. For example, from day to night, you can have a difference of 20 degrees Celsius in the temperature. Whereas climate is something that's long-term, so it has scales from decades to centuries and up to millennia, and it's very slowly varying. So, for example, the average temperature in the UK might vary less than a degree Celsius every decade. So if you were talking to a weather scientist or a meteorologist, you might ask questions like, will it rain tomorrow? Whereas if you were talking to a climate scientist, the kind of question they might know the answer to would be, are winters in 10 years likely to be colder than winters now? Now we've gotten very good in the past century at predicting weather. In fact, our weather predictions improve all the time. And this is a graph I've taken from the Met Office. And on the y-axis, you've got the error in their weather map. And on the x-axis, along the top, you've got dates. So it's quite small. If you're at the back, you probably can't read it, but the dates go from 1967 on the left to 2007 on the right. So you're spanning 4 years. And these different lines show the error in different weather forecasts that the Met Office produced. So the red line is the 24-hour forecast, which obviously has the smallest error, compared to the 48-hour forecast in blue and the 72-hour forecast in green. And so you can see the error has gone down over time, as you'd expect, as models improve. And you can actually see in 2007, the 72-hour forecast of 3 days will have the same error as the 2-day forecast from 1997. So, and if you put this forward to today, I don't have the data, but they're looking even better all the time. So that's great. But this is only really, our weather prediction is only really good up to 7 days or so. If you start to look further beyond weeks, that we quickly run into the problem that the climate system is inherently chaotic. And I'll quickly run through what this plot is, and hopefully I'll explain that. So this is a plot I've taken from the NOAA website. Now NOAA is kind of like the US equivalent of the Met Office. And what they've produced is a graph of sea surface temperature due to the El Nino phenomenon. And this is plotted on the x-axis against time from April 2011 to October 2012. And on the right hand, on the y-axis is temperature. And the black line is observations, which runs up to about February 2012. And then from then onwards, they run a suite of different models, all starting with slightly different initial conditions, and run them forward to try and see how that might change in the future. And you can see that in the first few weeks, they really are quite tight together. You've got a definite prediction, but as you go forward and weeks turn into months, each of the different models in this in colour are producing wildly different answers. This is, as I said, because the climate system is chaotic on longer timescales. And you may have heard the term chaos before. And what we mean in this context is that the system is very, very sensitive to initial conditions. And you may have heard that termed the butterfly effect before. And what this means is if you have a small difference at one time and you run your model forward, that difference won't stay small. It will grow larger and larger. And what this also means is that even if we were to have the perfect climate model that exactly reproduces the Earth in all its glory, which is, a big ask, but, say we could do it. Even if we could do that, if we couldn't measure the temperature and all the other variables on the Earth perfectly, we would still run into this problem, that small differences in temperature between the model and the real world would soon become very big. So a second reason why climate is harder to predict as well as weather is it's simply a computational one. We have limits as to how many computations we can do, and this is an example of the difference between a climate model and a weather model, looking at rainfall over the UK. Because weather models only run up to, say, 7 days, and you're only really interested in where you want to know the weather. So, for example, the Met Office has very high resolution over the UK because that's where it's doing its weather prediction. You can get very accurate rainfall measurements. Whereas if you're looking at a climate model, which you might want to run for hundreds of years over the entire globe, computational limitations mean you really can't do as well as this if you want your climate model to finish running within the lifetime of, say, your PhD student. You've got 3 years. So this is another reason why we can't do as well with climate models as we can with weather prediction. And then I was at a talk a few weeks ago that made the statement that if you were to trust Moore's law, which tells you how much computing power will increase over time, we're going to have to wait about 60 years before climate models are going to be able to get down to the resolution we'd really like. So, it's a good time to ask, what is a climate model? What does it look like? Well, here's a kind of simple depiction. The first thing to understand is that when we think of a climate model, we take the Earth and we think of external forcings, so things that drive the Earth system. And we can think of these into we can put these into two different categories. We can put them in natural forcings or man-made forcings. So the two major natural forcings we have is, first of all, the sun, obviously. So the radiation that comes from the sun changes our climate, and that can vary slowly as we move further or slightly closer towards the sun. And volcanic eruptions can also produce extremely large but very short-term effects on our climate. And then you also have other man-made forcings, such as us emitting greenhouse gases into the atmosphere, or more subtle things like land use change. If you take out a whole forest, it's going to change the climate system. So the climate model takes all these forcings, and it also takes the internal dynamics and simulates cause and effect. So when I mean internal dynamics, what I mean is what's kind of depicted here. So at each grid point, we've divided up the Earth into grids of equal size, and at each grid point is affected by these forcings, and it also interacts with the grid boxes next to each other. So this is why you need a model to understand all this, because all these different interactions can quickly mean that it's hard to predict what any changing something in one place in the globe will have an effect somewhere else. So really what a climate model is a set of mathematical equations that encapsulate these forcings and this internal dynamics. And they're computed at individual grid points. And so here on the right, I've just got a few depictions of how climate models' resolution, so that's how many grid boxes there are, has changed in time. So at the top you can see that it's probably quite small at the back, but on the left we had the vertical resolution in the mid-90s, where you had 19 vertical levels in the atmosphere and 20 in the ocean, and present day we're up to more like 40 levels in the ocean and 38 levels in the atmosphere. And here, this is a kind of depiction of how horizontal resolution has changed. And these are taken from the assessment reports of the IPCC, or the Intergovernmental Panel on Climate Change. So this is the horizontal resolution of the models that went into the first assessment report, the second assessment report, third, and AR4, which came out in 2007. So each of the different kind of components you can think of, like the air, the sea, and the ice of the climate system, all have their own equations which are coupled together. And more are added all the time as models get more complex and our computers get better at handling them. So this is a depiction of how what is included in a climate model has changed over time. So if we're starting in the top left in the mid-1970s, where really climate models were just an atmosphere. You had the solar forcing, you might have had a bit of moisture, and you could maybe model CO2, but that was about it. Over onto the top right, in the mid-1980s, people had added clouds, and there was now the interaction with land and a prescribed ice, which means the ice doesn't change, you just tell it there is some ice. By the first assessment report of the IPCC, it included a swamped ocean, so it has no internal dynamics, but we know there's an ocean. That's good. The second assessment report adding volcanic activity, sulfates, and the ocean now has some internal structure. By the third assessment report, we're adding aerosols, the full climate carbon cycle, rivers, and the ocean has an internal overturning circulation. And by AR4 in 2007, we've got interactive vegetation and very complicated chemistry. And the fifth assessment report, AR5, is going to come out next year or the year after, and the models that go into that are already developed, and they have much more detailed ocean and ice models, among other things. That's all right? Okay, so now we know a bit about what climate models are. What questions can they answer? Well, because none of them are perfect, we know none of them are going to actually tell us what reality is doing. They're parallelized in using them together. So they're very good at answering long-term average questions on climate timescales, such as looking at the average temperature of the planet. So here I've taken a plot from the last assessment report of the IPCC, AR4. And what's plotted here is a temperature anomaly. So that's the difference in the temperature between the mean from 1900 to 1950, over time from 1900 to 2000. So the black line his observations. All the orange lines are one of the 23 models that went into AR4, and the red line here is the mean of those. So that you can see, while if we took one of these orange lines on its own, it doesn't look too good. Together, they give us a very clear mean that is very qualitatively, so that means in how it looks rather than in individual numbers, a very good match to reality. And what you can see here on the vertical grey lines are significant volcanic eruptions, which we'd expect to produce significant spikes in temperature, which they have on here. So we can actually update this now. So this only runs to 2001, but recently some people have run these models forward to 2011. So this is a slightly different colours here. So here the black line is the mean of the models. The grey line is there where they think they're 95% sure the answer lies. And the different coloured lines are different data, so different estimates of what the real temperature was. So you can see that they're still doing quite well. They've been run from 2000 onwards, but 2011 looks a bit colder than the models predicted. However, we're pretty sure that that's because there was quite a strong La Nina event at the beginning of 2011, which made the Earth slightly cooler than the models predicted. So these two graphs give you a bit of an idea of the error from the models, but they don't really give you an idea of what the error in that data might be, or what the error might be in some of the data that the models themselves depend on. So this plot here is a bit more complicated, but it shows you what goes into these kind of models. So the top three graphs are the main three forcings that drive a climate model. As I said before, we've got volcanic forcing along the top, solar irradiance second down, and then all other forcings, which include man-made forcings such as carbon dioxide and other greenhouse gases. And this is against time from 1000 to the year 2000, so 1,000 years. And you can see that really other forcings didn't really come into play until the end of last century. So the different lines represent the fact that we're not entirely sure of what the volcanic forcings were in the past. So there's a few different data sets there. So there's a differences in some of the models might use a different data set to the other, and similarly with solar irradiance forcing. So on the bottom here is a bit complicated, a bit messy, but what you've got in colour is some of those different models that went into the last IPCC report. And so they have different combinations of the forcings shown above. And shown in grey is the temperature record. And the darker colour means that we have better overlap between different temperature records. So back in the year 1000, we really didn't have a clue what the temperature was. We've got quite a few different records that aren't very well overlapping. So I hope you can see from this plot that given the uncertainties that exist in the data, that the models are really doing quite well. And if we go down to a continental level, we can see they still do very well. So here, for each continent, we're looking at the temperature record again from over the last century, from 1900 to 2000. So the black line is the temperature record, and where it's dashed is where we're not too sure, we haven't got very much data. And the red shaded area is where the models, those 23 models, think that it's 95% likely that the answer lies for each continent. So you can see again they do very well. And for comparison, they've plotted here in the green shades, or the blue shading, what the models predict would happen were there to be no anthropogenic forcing. So if we didn't have any of those man-made forcings such as CO2 or methane, where do the models think we would have gone? So you can see there's quite a good separation between the two, especially as we get towards the year 2000. And on the bottom here, they've combined these into a global land and global ocean. And I'll just point out there's a bit of a spike here that doesn't look too good, but I'll come back to that later. So as I said, we know that none of these models are perfect, and none of them really represent the real Earth. But I hope you can see that they're parallelized in using them together, because they contain so much high, very good science about the dynamics of our planet. So this is an example of where climate models have been used together to tell us something that we maybe wouldn't have been able to know without the climate models. So it's a bit of a complicated graph, so I'll take it slowly. It's basically looking at measurements of snow albedo. And albedo means reflectivity. So the snow is white, it reflects light back out into the atmosphere. So what they did in each model was measure how much a change in snow albedo, so snow reflectivity, which could be due to melting, affected the temperature, the surface temperature. So they measured that on a seasonal difference, so checking from winter to summer, how much the albedo changed as a percentage of temperature. And then they also measured that over centuries, so a climate kind of scale. So they looked at how much the albedo had changed in the models over 2 centuries, and compared to that how much the temperature had changed. And then for each number here represents the measurement, so where each climate model from that suite, from the IPCC's 4th report lies, so 1 to 23. And you can see that they imply that there's quite a strong relationship between the seasonal cycle of albedo feedback and the climate cycle of albedo feedback. And so while none of these, or maybe only 3 of them, lie anywhere near to what we estimate the real seasonal cycle albedo is, together they provide quite strong evidence, and we might be able to tell something about the climate albedo feedback from this. So this is by no means proof that there's a link between these 2 quantities, but it does provide the first step for scientists to go look for this in the real Earth system. So finally, a little caveat that data, while none of the models are perfect, our data isn't perfect either. Here I'm plotting sea surface temperature record and the land surface air temperature record going back to 1880. And there's this bump here in the 1940s that's mystified scientists for quite a while. So all the vertical grey lines are again significant volcanic events. So we can see some other jumps that are associated with volcanoes. And also in this record we've removed the signal of El Nino, so we know it's not to do with an extreme El Nino event. So it was actually discovered in a paper that's published this year that the reason for this dip is due to a change in measurement methods in 1945. So up until 1945, sea surface temperature measurements were made by US ships who measured the temperature of the seawater that they were taking into the engine room to cool their engine. So you can imagine that has a bit of a warm bias. And in 1945, we switched back to using the UK sea surface temperature measurements. And on UK ships, to measure the sea surface temperature, they would drop a bucket over the side and measure the temperature on deck. So you can imagine that going from one to the other will produce a spike like this. So now that this has been identified, it will be corrected in the records, and in the next assessment report you will see this kind of difference. So I thought it was just a nice example of what here, actually the models were doing quite a good job, even though it may have looked initially like they weren't representing the record. Alright, so I'll bring it to an end there. I hope I've explained to you what a climate model is. And while we know that all climate models are wrong, I hope you'll agree that some of them are useful, and that if you ask the right questions and use them together, they can be very powerful. And I'll just end on finally just saying that they are improving all the time, and so look out for the next assessment report, the IPCC, which will be coming out next year or the year after. Thank you.
Fantastic. While Erica gets her presentation up, I'm just going to move a couple of the shares towards the back.
So, I'm going to present the opposite view, debate style. Now, there's a disclaimer I want to make before I do that, which is that these views are entirely my own and they don't represent necessarily those of my institution. Because I'm going to talk about a few technical criticisms of climate models, but also some more political criticisms. So I think one of the reasons that scientists are often scared of saying interesting things is because they're worried that they'll be quoted out of context. So the disclaimer says, please don't quote me out of context. So I'm a climate scientist. My PhD at Imperial is on North Atlantic storms, and I'm looking at a hierarchy of different models and what information we can get from those different models about the climate of the North Atlantic, how it might change in future, and what confidence we have in our predictions of the change in the future. So I wanted to sort of say straight off that despite I'm arguing against climate models, typically that comes from people who are sceptical about climate change. I'm not at all sceptical about climate change. I think it's a real, very serious problem. I think, obviously, the CO2 that humans are putting into the atmosphere is a problem and is causing climate change. So just to get that out of the way, in case anybody is under any illusions that being critical of climate models goes with a sceptical view about climate change, it doesn't necessarily. And this is probably a minority view, but I think it's an important one to understand. So what I'm going to argue is that climate models are actually counterproductive, that they're hindering meaningful action on climate change, which is a serious problem. So the question is, what are climate models for? And there are several answers to that. The one I'm going to focus on today is that climate models are for providing information to us, to individuals, to households, to decision makers, to policy makers, to businesses, about what the future climate is going to be like, and therefore what decisions they should make about how they conduct their business, or where they choose to live, or what they choose to do, that sort of thing. So I think it's all about risk, and it's all about the uncertainty as well. We want to know not only what the prediction is, but whether it's going to be right, how good it's likely to be. So one of the key questions is, how do we know whether the models are any good? And if you ask a climate modeler, they'll come up with three answers. One of the ways that we check whether our climate models is any good is by comparing the model results with real climate observations. So that was one of the things that Emma showed, was about how the models agree quite well with 20th century climate. So we put in the data that we have, and we say, how well does that agree with the models that we have based on the data? So they may have been calibrated on the same data, so that's a slight statistical problem, but it doesn't invalidate the conclusion that actually that is a source of confidence in the model. If it got it really wrong, you'd think it was rubbish. Comparing model results with each other, so Emma mentioned that at the end, that we don't just use one climate model, we use lots. And if they agree with each other, then again, that's really encouraging. They got the same answer, probably for different reasons. Hopefully for the same reason. It's sort of like solving a problem in maths two different ways. If you do it two different ways and you get the same answer, you think, yeah, I'm confident in that. And the third reason is the models are based on physics, and we have confidence in physics. So we derive the physics by theoretical and experimental work, and we then put all of that together into the model. So those three reasons. But what I'm going to show today is that they are good reasons to have some confidence, but they are not rigorous justifications for having full confidence, and we should be aware of the limitations. Okay, so I have three arguments. One is a mathematical argument, that we have misunderstood the nature of uncertainty, or we haven't fully understood the uncertainty that is inherent in climate modelling, and that we're therefore underestimating the level of risk, because we're underestimating the spread in projections in the future. The second is a practical argument that, as Emma showed quite nicely actually, climate models don't really tell us what we want to know. And the third is a political argument, that this is where scientists aren't supposed to have an opinion, but I do have an opinion. I think that actually the focus on modelling is a distraction from the real problem of climate change. So I'll talk about that as well. Okay, so Emma talked about the butterfly effect. Thanks for introducing that. So is everybody happy that the butterfly effect is a description of dynamical instability? That if you have the initial conditions slightly wrong, then you project your model forward and you could go off in a completely different direction, and your solutions after 100 years might be totally different. Yeah, so that's the butterfly effect. So what I've been looking at is something which is quite similar, but it's structural instability in models. It's the difference between one model, which is constructed from one set of equations, and another one, which is very similar, but with very slightly different equations. So it might be the same equation plus 0.0001 times x. So almost the same equations. Now if you run those forward, actually what you find is that the behaviour of those equations can be totally different. That they end up with not just a diverging trajectory, but a diverging landscape of the climate, the evolution of the system. So you can have completely different behaviour of solutions. So I've decided, because the butterfly effect is such a nice catchy name, that we should call this the Hawkmoth effect. So here's a hawkmoth. It's a native British moth, so I think it's rather pretty. This is not actual size, obviously. They're about that big. They're very camouflaged. It's not an easy thing to spot, is this structural instability. They're also ugly and unknown. So I thought they were quite a good sidekick for the butterfly, which is well known and very, positive and attractive. So a statement of the Hawkmoth effect is that we can be arbitrarily close to the correct equations, but still not be close to the correct solution. That's this structural instability. You can have equations which are right all the way down to the end and then plus 0.0001x, but that, because of all the feedbacks in the system, that has an effect on everything else, and that makes the whole behaviour of the system turn out different. So that has quite a lot of consequences. If you think about it, what you're doing when you add the 0.0001x is something like you're approximating the system. So you're trying to make an approximation of one system with another. And if you've missed something, which is really, really small, normally what happens in physics when you have a really simple linear system, maybe you have a pendulum which is swinging, or you have, you have a sort of snooker table. If you make a very small error in your equations, that results in a very small error in the solution. And that's what we're used to as physicists. So my undergraduate degree in this fine city was in physics, and we spent a lot of time measuring G. And when you do that, if you make a model, you assume that a good model, which is close to the correct equations, will give an answer which is close to the correct answer. And we did that lots of times. And so when you have a simple system, you make that approximation, and it is the case that your approximation is useful. But the climate is a completely different beast, and complex systems are a completely different beast. Think of biology, think of economics. The climate is a many-dimensional complex system with lots of feedbacks, lots of non-linearities. Many aspects can't be approximated in that way. The hawkmoth bites. This is the problem, that when you make that approximation, even if your approximation is almost arbitrarily good, your answer may still be arbitrarily wrong. So comparing with observations, which is one of the things that gives us confidence in models, may not be very informative about what was wrong with our model. So just use the example, if you did have a really simple system, a simple pendulum or something without any feedbacks, then you might make a model, and you might then go and take some observations, and you'd look at a graph like that, and you'd say, okay, I can look at that, and I can say, it's quite clear to me that the error is informative about what is wrong with my model. So I would go away and I would say, I know exactly what I'm going to do to change my model to make it better to fit those observations. Yeah? In climate science, So this is an example from my research from North Atlantic storms. This is the track density of storms over the northern hemisphere. So there's the US, there's the UK. And this is the difference between a climate model run with historical forcings and the real climate over that period. So it's a reanalysis actually, but it's close enough. And you see that there's so much structure in this. There's so much going on. How do you go back to that and say, oh, well, it's obvious to me that we've got the topography of Siberia wrong? You know, you can't do something like that. And you can't go to it and say, oh, well, it's obvious that we need to turn up the entrainment coefficient or twiddle one of another knobs. Because actually, what you're doing by producing this graph, you're taking one extremely complex, many-dimensional dynamical system with nonlinearities and feedbacks, which is the real world, and you're subtracting it from another complex dynamical system with many dimensions, nonlinearities and feedbacks, which is your climate model. So you should expect that the difference of those two will be another many-dimensional complex dynamical system with nonlinearities and feedbacks, and you'll get something horrific like this. And then the reason that we make climate models is because we can't understand pictures like this directly. We can't go back straight and say, well, it's obvious that, you know, I've got the topography wrong or something. So what this means is that it's then very difficult for climate model development to happen in a sort of rational and progressive way. You can look at things like this, but then actually in practice what you do is you go away and twiddle a few random knobs and try and get it to look better. So model development is really hard. It's not really a science, it's an art, and I don't think that's very well appreciated. You do just go away and twiddle a few random knobs, and maybe you have some kind of hunch about what would be a better one to twiddle than the other, and probably that's related to which ones you thought were worse to begin with. So you can't rely on agreement with observations, because it could be very different even if you actually had it quite good. You can't rely on agreement with other models, because they might be right for different reasons or wrong for different reasons. They might all get the same answer, but that's because the people that made them were people who had worked together before and were using the same equations and had started with the same dynamical core. So you end up with something very similar. And they want to get into the IPCC report, so you know, if the North Atlantic happens to be frozen in your model, then you go back and do something else before you submit it. Obviously. And you can't even rely on the physics, because for the same reason, the Hawkmoth effect, if your physics is arbitrarily good, your model may still be arbitrarily wrong in the solutions. It's a pity, but it's true. So you may have missed something small. It may turn out to be very important. I'll give a few examples later. I also think this is key, that as models get better, so as we start to understand more of the uncertainty, it's likely that our estimate of uncertainty will increase, not decrease. So there's this idea of science and the IPCC and all of this sort of progressive scientific progress, that we will get better, that every time we add more things into the equation, every time we make more observations, every time we improve our model in the physics, that we'll get an answer which is better and closer to the true answer, and that we have a better idea of what the climate will be like in 100 years' time. But I think that is not necessarily the case, because you start off by modelling the things that you understand really well, obviously. And then you move on to modelling the things that you don't really understand, or you don't really have observations of, or you don't really know much about it, but you think it might be important. So you start putting it in. And as you do that, do you really expect that the uncertainty will go down? I don't think so. I think you expect it to go up. So hopefully you're learning more about the physics, and you can constrain better the things that you did previously. But as we keep adding more and more things, I think it's by no means guaranteed that uncertainty will decrease. And I think that's a problem for communication as well. So that's the mathematical argument. Here's a practical argument. What climate models are great at is what will happen globally and what will happen to the average. But nobody was ever killed by global mean temperature. Nobody actually cares about global mean temperature, apart from the politicians, because it's a really convenient number to sign up to. What we really need to know, and what we are actually, as individuals, households, businesses, governments, etc., interested in is what will happen right here and what will happen to the extremes. If the climate model says that the temperature over the whole world is going to increase by 2 degrees in the next 100 years, well, that's interesting, but it doesn't really mean anything to me. But if you say the temperature in Cambridge is going to increase by 2 degrees in the next 100 years, that's more useful. But also really what I'm interested in is the extremes. If you say the temperature in Cambridge is going to increase by 2 degrees, and that means that the extremes will change as well. So instead of having, two days per year over 35 degrees, we'll have 20 days per year over 35 degrees, something like that. Then that would be really interesting, especially if I was an ice cream seller, or an elderly lady, or somebody with an investment in a nuclear power station. Those sort of things would be really interesting. So what we are most interested in are the things that the climate models are least good at. Now here's the political argument, the slightly controversial bit, so don't quote me on these. I think that climate models are quite bad for science in a way. I think that because every time we have a new round of the IPCC, that leads to guaranteed publications for everybody going back and doing exactly the same thing as they did 5 years ago on the new model, the latest model. I think that leads to people getting very model focused rather than impact focused. I think we end up doing modelling for modelling's sake and not for the sake of what it actually tells us about the real climate system. I also think it ends up with people who are better at understanding the Fortran than they are at understanding the physics. I think that's a real shame. I think that because it's very easy to get publications out of climate models, it becomes less easy to get publications out of standing back, taking a step back and thinking about the climate models. I think that's a real pity. People like my supervisor are fantastic. People who were there in the 1960s, 70s, 80s, and who developed the models. He wrote the first dynamical cores from scratch. That's really useful. That's a real insight that he has into how those models work. But I use these models. I haven't worked on any part of them. I don't know really how they work because several hundred people have worked on these models. And while I could go away and research how each individual bit of it worked, I still wouldn't know how the whole thing behaved because it's such an emergent property, the behaviour of that climate model. So I think we need to go back to the physics bit. I think that would be really useful. Coming back to the uncertainty side of things, I think that, because of what I said about the Hawkmoth effect, this lack of attention to uncertainty narrows the spread. That we've captured really well a few specific types of uncertainty, and one of those types of uncertainty is the uncertainty when you twiddle all the knobs, so all the parameters. So there are multi-parameter ensembles, perturbed parameter ensembles, where they say, well, what happens if we perturb each of these, and then we'll do all of those, and then we'll get some idea of the range. So that's one way. And then there's the multi-model ensembles, where you take the model from the Met Office, and the model from the Max Planck Institute, and the model from Japan, and the model from the US, and you put them all together, and you say, well, these are all different models, and what's the range that we get by doing the same thing with each of those? And you get another range there. But I think we've missed the big one, which is the epistemic uncertainty about how the model is actually related to reality. And I think that's a really critical one. And I think that actually that leads, it's not really quantifiable. It's a really hard one to get at. And that's why it's kind of been ignored, because it's something that's quite difficult to actually quantify. But it's something that is likely to have a really big effect. And if you ask climate modelers, what are the uncertainties that we haven't included? The things that they'll say are the dynamics of ice sheets, or ocean circulations, or the dieback of the Amazon, or sort of the Sahara, these sorts of things. Methane in Siberia, methane release, these are things that are not really in the climate models, or if they are in, they're only in very simplistic ways, and we know that they're not adequate. So we can even see where the sources of this uncertainty are coming from, and yet we're still on this straight and narrow path of saying, well, the uncertainty that we can quantify are these uncertainties, and this is the amount. but there is another uncertainty. And I think as we get better at understanding uncertainty, then we will start bringing more of that epistemic uncertainty into the known uncertainties. So we'll take the unknown unknowns and bring them into known unknowns, and our uncertainty will increase, but we will know more about the climate system, so that will be a good thing. But this is never acknowledged. All of the sort of funding calls, that sort of thing, are always for decreasing uncertainty. You know, I want to see a funding call for increasing uncertainty in climate models, because I think that's what's going to happen. And I think actually, if we don't acknowledge that this is going to happen, we run into problems, because if the IPCC says 1 year that the uncertainty in sea level rise is this much, and in 5 years' time they've gone away, they've been funded a lot of money, and they've gone away and they've done lots of research, and they come back and they say, well, actually, our uncertainty hasn't changed very much, possibly it's gone up a little bit. Then people start saying, but we gave you loads of money, what on earth have you been doing in those 5 years? Well, actually, they've been doing really useful things. They've been understanding more about the science. But it looks bad to the public if you say our uncertainty has increased. People say, does that mean we know less than we did 5 years ago? It doesn't mean that. But we need to start accepting that that's how it will look. Another political argument. This focus on 2 degrees, especially, global mean temperature, I think it's a useful variable, because it allows us to compare between all the models quite easily, and it gives a handle for people who are not scientists to think about it. But I think it trivializes the debate in quite a dangerous way. I think, for instance, that the focus on global mean temperature, if you say, well, the temperature will increase by 2 degrees by 2100, say, whatever, then people will start saying, but if we did geoengineering, putting aerosols up in the stratosphere or mirrors in space, then we could bring the temperature back down by 2 degrees. And then we've solved the problem, woohoo! Well, but we haven't, because actually there's a big, big difference between the local and extreme effects, the patterns of effects, between what happens when you put CO2 into the atmosphere and the negative effect that happens when you put aerosols up in the stratosphere. It's not, by any means, the opposite. So you won't get back to something that's exactly the same. You get back to a planet with exactly the same global mean temperature, but a totally different pattern of precipitation. That might be a problem. The other thing, models, I think, are quite over-conservative. I could go through some examples if you want me to. But I think it's essentially just this, non-covering of the epistemic uncertainty. I think we really underestimate the probability of something nasty happening, what Lenny Smith calls a big surprise. So we think that the risk is small. It may in fact be larger than that, so we don't really necessarily understand what's going to happen. So a good example is the European heatwave in 2003. That happened, and it was something like 4 standard deviations above the normal range of temperatures for that time of year for Europe. Now, that was totally unprecedented. It was something that happened, and people then said, oh, wow, well, but our climate models weren't predicting an event like this to happen for at least the next several decades. But it did happen. And the reason it happened was because the soil moisture processes were not very well modelled in the climate models. And what happens is that when the soil moisture can evaporate and it takes heat with it. So at the point where you've evaporated all of the water from the top layer of soil, there's no more water left to evaporate, and therefore no cooling effect left. And so you get a little bit of non-linearity. And so it can go further than you expect for the same forcing. So what happened after 2003? Well, obviously everybody with a climate model went back and said, right, soil moisture is really important, let's go and put it into our models. But what else is there that hasn't happened yet, that we don't know, that we thought wasn't important? Soil moisture we didn't think was important, so it wasn't there. What else is out there that is important that we don't know about until something nasty happens? There might be things. How long have we got? Your negative things. I get there. I'm committed there. I think that if this idea that uncertainty will be reduced encourages people to wait until the science is settled. If we wait until the science is settled, I think we'll wait forever. So we need to get on and do something now. People will then generally say when I give this talk, well, what on earth should we do? Good question. I think we should keep doing climate modelling because, as Emma said, it's really important for us to understand the physics. So we do the climate modelling, the climate modeller at his or her desk, playing around with it, having a go, seeing what happens when you set off a gigantic volcano in Indonesia. That is really important. We need to understand the processes. So climate models are important, but we shouldn't necessarily use the outputs directly for policy making. If you want to know the answer to what is going to happen in 2100 to some process that's of interest to you, don't ask the model. Ask the person that made the model, because they will have the insight about the model. They will be able to take the answer that the model gives them, and they'll be able to tell you what the model doesn't do, what might be out there that we haven't included. So that's more useful. We should also invest in observations as well as models. One of the things that's a problem right now is that we are not taking observations of the deep ocean temperature in the way that we did in the 1960s. So why are we not doing that? That's something that's going to be incredibly important in the future. If we have a gap in the record, it will make it really difficult to tell what's going on. We should start adaptation now. There are obvious things that we ought to be doing, like using less energy, insulating our houses. And for adaptation strategies, we should be looking at things with flexibility and planned reassessment rather than things that we can do now and forget about. So to finish, the future will be zero carbon, whether we like it or not. So we might as well do something about it regardless of climate change. I think climate change is going to be an extreme problem for the next century. But there are massive uncertainties on it. We don't know exactly what's going to happen. There are many things which we can solve by taking the same sorts of actions. So let's get on and do those. That's all.
Thank you very much, Erica. So I'm going to ask Emma to come up as well. Now, because we're getting close to 2, we actually have the room booked for a bit more time. So I think what I'm going to do is run on a bit. If anyone absolutely has to go by for 2, then now is your opportunity to do it very quietly. But anyway, we're going to start taking some questions now. So, yeah, go.
I'll wait.
Right, let's go for it. Go ahead.
Yes, a very naive question. What exactly do you mean by global mean temperature?
Great question. Yeah, I'm not sure actually.
Is it the mean of all the temperature you've taken at weather stations around the world, like 1.5 meters above the ground, and you with a shaded box, or what?
In terms of, so when we talk about observations, that's one thing I don't have time to go into too much detail, but you mentioned as well, is that we don't have a thermometer at every metre square over the planet, and at every level as well. So what we do is we take all the measurements we do have, and they put them through a process called reanalysis, which basically means let's make it look like an output from a climate model so that we can compare it nice and easily. So let's put it all on the same grids, and that requires you to make assumptions that are similar to the assumptions that go into models about how, if we didn't know the temperature, if we do know the temperature here and here, what's the temperature here? So that also requires some modelling work. And so that means that there are uncertainties in what we mean by global mean temperature as well.
That also implies, I think, that you've got to make some allowance for the different times at which all these models are, these temperatures are taken, and also what extent of that surface each one of them is valid for, if it's valid for anything other than the point at which it's taken. So have we really got a global mean temperature?
Well, we have a global mean temperature, but it has an uncertainty on it.
You can mathematically define it, whether that means anything philosophically.
Yeah.
Stop plotting graphs of the moon.
A mean temperature doesn't mean much anyway. It'd be better to think about it in terms of heat if you're thinking more physically. But I think it's a reasonable measurement.
You think it is? Okay. Thank you.
I don't have any problems with global mean temperature. I think the uncertainty on that.
Well, it's a question of
There are quite a lot of observations.
No,
I think there are other problems.
Yes, we see lots of global mean temperatures, 2 degrees or whatever.
Yeah.
We very, as you say, we don't look at extremes, and also the distribution
Yeah.
Because a shift in the distribution, 10 degrees warmer and 10 degrees colder, but not in between,
Yeah.
would be quite different than, so unless you can look at distribution, and yet I've never seen that in any of the literature.
Well, climate models will all produce distributions of extremes
I'm sure you
and
can get out of them.
Yeah, I mean, if you
It's only
a
like
good climate modeler will be looking at statistics rather than numbers. And a problem also is that scientists think that the public can't understand statistics.
Well, maybe
And they're not very often
already, but yes.
they're very often very badly explained,
Yes.
and so they like to avoid giving the statistics, which often makes them seem like they only think about reading global temperature, when really if they're a good climate scientist, they're looking at the statistics.
yeah. They're certainly available.
Just go, gentleman at the back.
Right, so I'll try to find something halfway between your two positions. And it has to do with Heidegger, who we're going to put aside all his nastiness for just a moment and just focus on one aspect of Heidegger, who talks about Newton and Cambridge. And what he argues is that with Newton, the empirical side and the modeling side sort of falsely split, that he doesn't think Newton should have caused that split. And what Heidegger argues is that the purpose of the model is not the prediction. The purpose of the model is to guide you in learning about the world through experimentation. So it's not actually, should I be empirical or should I be a modeler? He sees them as the same kind of an activity. And to a certain extent, in the IPCC, we've, I think, mistakenly made that split that Newton never intended to make. So is that pushing together at all? Or?
Yeah, I think so. I certainly agree that I don't think the model on its own tells us very much, but I think the model in combination with the people that made the model and why they made the decisions they made and what they know they've left out, that is important.
Yeah, I definitely agree.
So, Emma, you mentioned a number of times there were 23 models with the IPCC, is that correct?
Yeah.
Are they still going forward with 23 models?
I think the same ones are all going in. I'm not sure.
There's probably a couple of extra.
So are we talking about the same models that's been modified as time goes on? Is that
There are different hierarchies of models. There was a great paper just last year constructing a phylogeny of climate models. So it was how each of them are related to each other. So there are several different models from the Met Office. There are several different models from other modelling centres. And you can see how each of them are related to each other and then how they're related further up. There are two main classifications of climate models, and that depends on the representation of everything within the model. One is a spectral model, and one is on a grid. So the grid ones are the ones that just have grid points, and they do everything on the grid points and then work it out. And the spectral models decompose everything into spherical wave functions, so Fourier series.
Yeah, if you've ever heard of Fourier series, it's similar to that.
Basically does that. So there are sort of two main tracks, but then within those they're all related in different ways. And they're all based on the same physics.
What I wanted to ask is, most of the model, I think, must be based on the NASA projection, and most of them are talking more like things that are happening in Europe or in America. They're not talking too much about the climate change in Africa, like when there are drought or when they will have flooding, for example, in order to save them or to help them with their farming or how to keep their food. The most information, I don't think they're getting some of those information. Why is that?
It's definitely a problem. I agree. I think that it's just a result of the fact that people think that people want to read about things that are interesting to their local, so people at the University of Cambridge think, well, people will be interested if I talk about the UK. And there is going to be more money available as well from the research councils in the UK and US have a lot of money compared to specific research bodies in Africa. So it's really unfortunate. And I don't think it should be the case, but it's a result of setting up a system where people get rewards for jumping through hoops set by certain funding bodies. You're going to get more people trying to jump through that hoop.
I think it is improving a bit. I think part of the reason is historical, that actually the areas where people started doing modelling the most were the areas where there were long time series of observations. So in Britain and Europe and the US, there are time series going back several hundred years because ships had to take ship's logs and vicars had weather stations in their gardens and they wrote down assiduously every single day what the weather was like. So it was a natural starting point, whereas places like the middle of Greenland or the middle of the Sahara or most of Africa, sadly, are places where there actually is not much long-term data, so it's less well understood anyway.
And when I'm looking at the weather forecast, I could see that it's the heat of the warm coming from west of Africa going to UK with the heat, like in 2003, the heat wave. It's most of the heat were coming from West Africa, from Africa. So if they predicted the weather from Africa, they would be able to predict the weather from Europe as well, as the same they predicted from Eastern Europe when the wind coming and we get the snow or the cold coming here. That's the reason we having is an unsettled weather in UK. If we were looking more down to, I think, West or Africa, we would know pretty well how the weather would look like in UK maybe in 50 years time. I think that's my opinion.
Definitely, I think
they shouldn't only stick in the Antarctic, but come down as well and do more research.
Yeah, I mean, if the Met Office had unlimited funds, it would cover the world in tiny grid points and make the best weather prediction it could. Unfortunately, everybody's limited, and they've decided to put their eggs in a basket that looks closer to Europe. And whether that's the right decision or not is debatable. It's obviously in some situations it's not going to help you, but they've decided that for most of the time that's going to be what's going to get them the best weather prediction.
But I think it is happening. I mean, it's getting better because it's becoming easier, less computing time is required now than was 10 years ago to do your simulations over the whole world rather than just Europe. So it's definitely happening. People realise that it's important.